In this video we're going to be introducing the concept of vectors. We're going to look at what a vector is, and we're going to sketch something called the resultant of a set of vector operations. If you've never seen vectors before, the notation can look a little bit confusing at first, but don't worry, the actual concept is really quite simple. A vector is just something which has a magnitude and a direction. This is opposed to something called a scalar, which just has magnitude. So for example, if we had the measurement 5 centimeters, that is just a magnitude, so it's a scalar. But if we said we're going to move 5 centimeters to the left, well, you see that's got a magnitude and a direction, so that makes it a vector. Another example, we could move at a speed of 4 miles per hour, and because we've just got a magnitude, we say that's a scalar. But if we moved at 4 miles per hour in a direction, let's say northeast, then we have our magnitude and direction, and so it becomes a vector, which is the velocity vector. Before we look at any more vector examples, we need to look at the notation we use to describe vectors. Vectors are always shown as an arrow pointing in the direction of the vector. In some cases, like this one, we mark out the starting point and the end point of the vector. So in this case, the vector A to B. And we'll write this A, B, and an arrow on the top of it showing that is the direction from A to B. And so if we reverse the direction of the vector and we're travelling from B to A, we would just write the vector of B, A, and the arrow travelling that way. A second way to describe vectors is by just putting a lowercase letter next to the vector arrow. Something which is really important to note is that the length of our arrow tells us the magnitude of the vector. So by working at the magnitude and seeing the direction, we can get both parts of our vector. So if you followed that, here's a simple example to show you some vectors in real life. So this is the riverboat problem, and we've got our little boat and it wants to cross this river. So it sets off to try and cross straight across the river. So the movement of the boat, we'll call that vector A, and we'll say it moves at 10 miles per hour. But even though the boat has set a course going across the river, the current is moving downstream, and we've signified that here as vector B. And we could say the current is moving at 5 miles per hour. Now the problem we need to solve is, what is the velocity vector of our riverboat if it's travelling 10 miles per hour across the river and the current is pulling it 5 miles per hour downstream? Well, to answer this question, what we do is we put the vectors end to end like this. So we have vector A connected to vector B. So the velocity vector of the riverboat starts at A and finishes at the tip of B, and we call this the resultant vector, and we'll call this C. And C will be the direction and speed which the boat will travel across the river. And that's why if you are sailing across a river, you'll usually have to set a course a little way upstream to make up for the current going downstream. Now, a little interesting thing about this particular question is you can actually find the magnitude of C, because if you look at this, in this particular question, there is a 90-degree right angle between the two vectors. So we have side A, B and C, so we can use Pythagoras' theorem to work out the magnitude of C. So if you want to just see if you can do that, and then we will look and see if you got the right answer. So the resultant velocity is 11.18 miles per hour. Now vectors won't always be at right angles to each other, like in the riverboat question. But finding the resultant vector is actually really quite simple. So in this case, we've got two vectors. We've got vector D, which is moving in a direction which is 1, 2, 3, 4 squares across, and 1, 2, 3 squares up. And we've got vector E, which is moving in a direction which is 1, 2, 3, 4, 5 squares vertically, and 1, 2, 3, 4 squares horizontally. Now, to find the resultant of these two vectors, all we do is simply redraw them, but with E following on from D, and I'll show you what I mean. So now I've drawn vector D, followed by vector E, following the direction of the arrows, and so my resultant vector starts at the start of D, and is a straight line from the start until the end. So you can see my resultant vector, which I'm going to call F, is 1, 2 squares down, and 1, 2, 3, 4, 5, 6, 7, 8 squares horizontally. We should also note that it doesn't matter whether I started with E or with D. If I'd drawn E, then added D, we would still get the same resultant. The most important thing, though, is that we must follow the direction that the arrows travel in. Draw these two vectors out in your jotters and see if you can work out the resultant vector. So if we add h to g, we get a straight line vector, which is 1, 2, 3, 4, 5, 6 squares along horizontally. And we can call our resultant vector g plus h. So now you can find the resultant of vectors such as g plus h. But now what we're going to do, we're going to extend this so we can find the resultants of multiple vectors. So what if we had the resultant of 2g plus h? Well, the answer is it's still just as simple. What we do is we find two lots of g and then we add the h to it. So here we've drawn g once, g twice, and h here, and so our resultant vector starts at the start of g and goes in a straight line all the way to h. So we have a line which is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares horizontally, and 1, 2, 3, 4, 5 squares vertically. Now try this yourself with 3g plus h, and then with 2g plus 2h. Here is 3g plus h, and here is 2g plus 2h.